of course, for these type of analysis, you look at input resistance, you look at voltage gain, and also eventually you want to look at output resistance. So the output resistance is the same. If you want to look at R out, you can do the same exercise. The equivalent circuit will look something like this. RS. This is GM VGS. RO. So the overall resistance will be something looking, this is the R out. But typically what we do is that we look it in from here. This is RO prom. So your overall R out should be RD in parallel RO prom. So let's look at the output resistance when we're looking down. This is basically what it is. Sometimes you will see representation like this. RSRD. If this is the RO, so this is referred to as RO prom. And if you're looking in from the output terminal, that's our out. That's what I meant by these two terminals where you are expecting your output resistance to be. Okay? So let's look at RO prom. So you can do the same exercise by having, the way to do this is right here. I'm just going to block that part out. So this was simply by giving a test voltage looking at its test current. So if this is the case, we can then assuming that my Vx will be voltage across RO. So voltage across RO will be Ix minus GM VGS. The current, the branch of current that's being left on RO times RO plus Ix times Rs. The reason why is Ix Rs because this is the only branch of current coming down. It's the same branch of current. Right? So I know Vx. So this will then give me, and then the other thing is that you want to know what your VGS is. VGS is, because input is grounded, therefore VGS plus this voltage drop, VGS, equals to minus Ix Rs. Right? Is the voltage across Rs. This plus this equals to 0. That's how we get this. We're going to insert this back in, and then you get Vx equals to Ix 1 plus GM Rs RO plus Ix Rs. So all of the terms are in Vx Ix. By definition, the RO prom, because we're testing at this terminal, which is Vx Ix, by definition, test voltage divided by test current. So the equation will look something like this. I'm just going to make sure I've got it right. So you get all the Ix to the left will be, let me write it down. Ix to the left, what is being left is 1 plus GM Rs times RO plus Rs. Okay? So you can rearrange it so that it looks differently. So you can have RO 1 plus GM okay? So depending on whether you want to express it in terms of Rs, the manipulation of or amplification factor it has, or you want to rearrange it this way, either way is the same. But the reason why at the end, we typically want to arrange it this way is because this is how much amplification. This is the same as the effect when you're looking in resistance, when you're looking in from this is when you're looking from here, how much amplification there is of this RS. It's being amplified by a negative feedback loop. So that is why typically it's arranged in this way. This is because of the negative feedback, that's why you have this RS being amplified by a factor of GMRO. GMR, 1 plus GMRO. Okay? You will see this type of amplification factor when you're looking down and also when you're looking up. There's an attenuation factor if you're looking in from here. So you will see the transformation of resistance when you're looking at the drain terminal or looking at from the source terminal. There's a inverse effect. Make sure I'm getting it right. Okay? So this is, so let me make a small conclusion on degeneration. So anytime you have degeneration, this is very, let's do a summary. So a little summary on common source stage. So for a single common source stage, it's basically two. One is this. RD, and then there's this. RSRD, EDT. Okay, we basically discussed these two type of structure. So this is the simple type. This is V and V out. So both cases, you would then have, because input resistance is very simple, for both cases, Rn equals to infinite. This is Rn equals to infinite. The cases in the left, there's no source of resistance, therefore your gain is basically, you can include RO easily. If you want to ignore it, it's fairly simple. So it's minus GM RO in parallel RD, right? And your output resistance is, on the left, is fairly straightforward. It's minus GM RO in parallel. It's GM. Okay? So on the right-hand side, it will depend on whether you want to include RO. The reason why I don't want to dump this whole thing in is that you don't actually see anything anytime you see this complicated equation. So typically what we want to simplify is that just to make sure that there's two stages. When you need to include it, when it happens, what is its impact? When you do not need to include it, you will see the main point. So I would still like to divide it in two parts. So Rn will still be infinite. This is when RO infinite. One is RO is finite. Okay? So when RO is infinite, you then have attenuation GMRD 1 plus GMRs. Okay? And the output resistance, as we said, the output resistance, you're only seeing RD. And on the right-hand side, we already know that if RO is finite, you need to include this 1 plus GM RO RS. Your source resistance being amplified, therefore your output resistance will be, the real thing should be, let me just be precise in case I don't make that. Just to be precise, should be this the whole thing in parallel RD, right? So if your RO is infinite, you will still return to this, right? And the ABO will be this one. Let me just write it down just for consistency. So it will be GMRO RS. Okay? So anytime, when you want to check whether if this becomes infinite, whether it returns to this, supposed to return, when you're assuming output resistance become infinite, then it should converge to this result. It should be consistent. Okay? Good. So that's a summary on common source stage. So you basically get a sense as to, it's just an amplifier. I want to emphasize once again, it's a inverting amplifier. It's typically used for, as I said, typically used for gain stage. It provides a good gain because it's a very good voltage gain, voltage amplifier because it has input resistance of infinite, relatively good gain, easily to control. And RS will then, the adding of RS is reduce, will reduce overall gain. Okay, voltage gain, or you can consider the reduce of transconductance. Okay? Good? I should say, typically referred to as the gain stage. If you're looking at, you can go in and look at most of the MOSFET I should say, most of the operational amplifier stage, they have multiple stages. The stage which will provide maximum gain is typically done by having a common source stage or a common emitter stage if it's a bipolar version. So typically this structure is used as the most simple gain stage. Okay? So let's move on to the next topic, which is the common gate. So this is also sort of, you can refresh yourself on the discussion of so to look at a common gate stage, what typically is being considered is this. I'm having the gate connected to a fixed bias, and the input is coming in here. And output is going out at this terminal. And there's, of course, some biasing component at the bottom. We just ignore that just for now. So your input is coming in at the gate, output is drawing out at the drain. That's a basic common gate stage topology. So we can also to analyze this characteristic, we're going to also look through the three key parameters: input resistance, voltage gain, and output resistance. And to get that, you basically do small signal model as well. Small signal equivalent circuit, I should say. We're also going to separate this in two stages. We're going to assume that first output resistance is infinite and the other is RL is finite. The reason why anytime you see this kind of assumption, why do we want to make it simple by assuming RL? Well, in this case, I can include it without too much hassle. Is anytime you have one terminal, so if I have an RL, the way to think about this, you see that very often. If I'm having an RL, we know that RL is here. So any one of the terminal is ground, then it's easy to include. Anytime either one of the terminal are ground, then include and does not include and cause a lot of complications because of the feedback sort of thing happens, because the bridge between the thing will affect the voltage and then it will feed back to the circuit. That is why it makes much more differences. If this is the case, if you want to include it, it's just a parallel capacitor, parallel resistance, so it's much easier. So it's more complicated anytime when there's no grounded, either one of the terminal is not grounded. So this also happened in common gate stage because if you think about it, the RO, both sides are not grounded. For source follower, it's easier because source follower, your drain is grounded. So it's AC ground. Therefore, it's much easier. So you will see complication only on degenerated source generation circuit and common gate scenario. Okay, so it will make, you would then need to analyze it in separate ways so that it will make the job, it will not lead to this kind of, it will lead to this kind of complications when both terminals are not grounded. Okay, so let's assume, let's do the version A. What did I use? Yes, I used I. Okay, let's assume this is infinite. So then your equivalent, just to get a bigger sense as to how the circuit works. So this is my input signal. And this is current, GM, VGS. And then I'm ignoring R out just for the first analysis. So this is the output terminal. This will be my input terminal. Input signal coming in, again, inputs coming in from source, going out at the drain. So if this is the case, you write down KVL. KVL is VGS plus V in equals to 0. This plus this equals to 0. That's your first equation. And then we write down our output voltage. It's fairly easy. It's still GM VGS RD. Okay? And by this equation, I know that VGS equals to minus V in. Therefore, you insert that back in. This will be GMRD. Therefore, I'm getting my AVO. Okay? So first, we get the voltage gain. The voltage gain is GMRD, which is a non-inverting amplifier. Okay? Let's come back and look at its input and output resistance. For a common gate stage, let's look at input and output resistance using this half page. So looking at the input and output resistance. So we're going to do the same thing. This is, when you're looking at the input, I'm giving a test voltage looking at its test current, GM VGS. RD. Okay? So if this is the case, this is looking at input resistance. I should say looking at Rn will then be Vx. We know that since this is your gate is grounded, therefore VGS is minus Vx. Therefore, Rn is Vx Ix. And what is Vx? Vx is minus VGS. What is Ix? Ix is this current, which is minus Gm VGS. Right? Let me highlight again. This is Ix going in. Ix plus the current coming down, which is Gm VGS, equals to 0. Therefore, you get the minus sign. And the other thing is that this loop, VGS plus Vx equals to 0. Therefore, Vx is minus VGS. So we get a very familiar result, which is Gm over 1. So anytime you look at the in from the source, you get approximately 1 over Gm as your impedance. This is typically fairly low and also can be changed. So for impedance matching by IDQ, by biasing, you can design and adjust by changing your device size and biasing current to make your GM to meet the level of whatever you want. So so let me write it down. So we get input resistance Rn, which is 1 over Gm, which is comparatively low. I should say, anytime I said this is a low impedance or low resistance node, it's typically in reference to all the terminals that exist in a circuit. So if you have a more complicated circuits, sometimes you want to pick the ones that has the lowest impedance, the lowest resistance. And this is the lowest resistance node. And typically, the source terminal is the lowest resistance node, meaning that it has large amount of current. Anytime you modulate, 1 over low resistance, meaning that if I modulate the voltage, the current itself required to modulate it is fairly high. That's how you get low resistance. So it provides high current node. So this is very important because once we enter the discussion of frequency response, you will see that low resistance node is actually much favored to deliver high frequency response because it has large amount of water to charge up whatever bucket that you carry. So that's a different thing. But just to get a sense as to why this is important. So comparatively, the reason why I typically refer this as a low resistance node is because it's relatively low. It's not definitely low. It's relatively low as to compare to other nodes in the circuits. So this is typically a low input. The structure provides a relatively low input resistance. So as I said, so this would then make it less favored as a voltage amplifier if you consider you have a source of resistance. We're going to talk about that a little bit. But this would then attenuate because it would then require a large amount of current. Therefore, it's not a good voltage amplifier because it would then internally drop certain signal onto the circuits. But it will then allow us to, as I said, allow us to do impedance matching, that sort of things, or to take in current signals. And we can also try output resistance. Yeah, we already did that a lot of times because if you ignore RO, this will be ideal, then this will simply be ideal. This is when we assume output resistance is infinite. So let me summarize again. So for a common gate, sorry, never mind. So for a common gate stage, when with RO infinite, If this is the case, then you get input resistance 1 over Gm, output resistance approximately RD, and then we get a voltage gain, non-inverting, once again, Gm RD. If you're using a voltage amplifier, two-pole model, that's the key characteristic. Okay. As I said, this is the model I'm going to use. So my two-pole model will look something like this, right? Rn AVO V1. This is V1, voltage drop on the resistor RD. Okay? So I could just simply use that 3 parameters to describe this overall circuit. So what if my source resistance, RS, so if you want to consider, so the variation of this is when one wants to consider the effect of RS. A source resistance is that at the source terminal, the input terminal, you have some series resistance at the source. So if I'm having a signal source, instead of having an ideal voltage source, let's say if this is my source signal, and then the source signal comes with a source resistance. So anytime you have source resistance, the impact will then changes. What happens is that it will then affect your voltage gain. Let's look at what its impact on voltage gain is if the source resistance is being incorporated. If this is the case, then your output, we're still looking at open circuit output, but the output voltage will be, we'll not consider the loading effect yet. So the output voltage will be AVO V1. We know that AVO is GMRD. So what is V1? V1 will then become Rn, Rs, Rn, Vs. Okay? So the actual gain, which is become output versus Vs, this is the revised gain when Rs is being included, will then become GMRD. What is Rn? Rn is no longer infinite. Remember, we're having common source. This is 1 over Gm. 1 over Gm. Okay? So this voltage dividing term will then allow a lot of voltage drop on the Rs because I have low input resistance. Therefore, you will get the overall gain, which is 1 plus Gm Rs Gm RD. You see something similar to this, but without an inverting sign. So anytime you have source resistance, it's a voltage dividing effect. It's the same voltage dividing effect, whether it's dividing under or dividing from here. This is ground, and you have to divide. Your voltage is being divided between VGS and RS. If your signal comes from the bottom or come from top, you get similar results. The only difference is just the sign, because whether you're moving in to improve current or moving to reduce current. Okay? So that's the impact of having a source resistance. It will also attenuate again. The main reason is because this is not a good voltage amplifier. You would then see significant voltage drop. Okay? So we have to then to look at the complication when RL is being included. The reason why this is very, we will need to address this. The main reason for that is because the main reason why we need this type of understanding is because common gate stage is not often used on its own as an amplifier. We're going to talk about that a little bit in the next, I believe it's the next section, chapter 9, I think chapter 9. Common gate is typically not used on its own. It's typically also stacked with something else. So in what we call the cascade structure is the bridging stage. So the transforming of the output resistance is very important, is to understand, let's say if I have a common gate stage. So to understand the effect of, let's say if this is the common gate stage looking like this. This is a fixed bias voltage at this terminal. Either way. You can call it VG, it's fine. So let's say this is my input terminal. This is my output terminal. So in our previous analysis, we're assuming that there's no linkage between source and drain. There's no relationship between the two. Now we need to include that. So we need to include the green part, which is there's a finite current. There will be a finite current. There will be a non-zero current between source and drain when the voltage changes. So when this is RO is no longer infinite, you want to include the effect. So this would then lead to some complication, not necessarily too much on the gain itself. It would then lead to complication as to when I'm looking in from here. If I'm looking down, RO prom. Or if I'm looking up, that's R out, R in prom. Meaning that I'm ignoring the effect of RS just for now. So there's a relationship between this Rn and RL in relation to its load. So this resistance will be amplified, will be attenuated if you're looking in from input. This resistance will be amplified, similar to the discussion of a source generation. So it would have different effects. We're going to look at that, the impact of impedance transformation. So common gate stage, if you include the effect of when when we consider output is finite, then it will lead to an impedance transformation, meaning that your impedance or resistance transformation in common gate stage. As I said, what I want to do is looking at the input resistance when I'm looking up. So your equivalent circuit will be something like this. If I want to, first we want to look at R in prom. So for R in prom, your equivalent circuit will be, this is grounded, gate is grounded. And this is VGS. You need to bear with me. There's a little bit tedious. RO. And it's connected to RD. Okay, so it's the green one. You're looking up from this terminal. If you're actually looking at the output, you have to include RS as well in parallel. Okay, so we're testing in from here. Vx, Ix. And this will give me R in prom. Okay, if I'm looking indirectly from the source. Okay? So if this is the case, you simply just write down the same equation once again. VGS plus Vx equals to 0. Right, if you're looking in from here, this loop will give you that. And what is Ix? Ix will be minus Gm VGS and minus, as I said, VL Vx RO. This is the current. So include two parts of the current. One is the current coming this way, and this is two sets of two branches. Yes.颠倒。啊，我哪里？这张哦，我写错了。Sorry. Your input, sorry, input is here. Output is here. Thanks. Okay? Thank you. So we're looking in from input terminal again, two branches of current. One is this branch, GMVGS. The other is the current through our output resistance. Okay? And then the last thing is that we know that Ix, this is the current, Ix is the same as this because this is a same node, right? So then we know that your output voltage, so by knowing this, I know my output voltage equals to Ix RD. So I'm going to give this into this. This is the only unknown, and then everything will be in it in terms of Ix, Rx. Okay? So you simply insert that, and then you get Ix. Let me write it down. So this equation will be Ix RO, everybody times RO. And because this gives me VGS is minus Vx. So I'm substituting this back in terms of Ix, I should say Vx. So this is Gm Vx RO. The reason why I'm just taking out the RO. And VL is Ix RD. So this will be a Vx minus Ix RD. Yeah. Okay? So this equation would then turn into that. Everybody times RO first, and then substituting VGS with minus Vx. That's what we get. Okay? So then we rearrange in all the terms with Ix on the left, which is RO plus RD. All the terms with Vx to the right, so which is 1 plus Gm RO Vx. So finally, go back to what we're actually trying to do is to find R in prom, I should say, which is Vx Ix. In this case, will be RO plus RD Okay? So this is the exact equation, but in most cases, we know that GMRO can be larger than 1. So this would then approximately by RO, RD, GM. Okay? So this would then become it's very similar to what we have done. So that is, if you look at the equation, what happened is that when ROs become infinite, you actually see this. You still see 1 over GM, right? And this is only when RO is not infinite, then this output resistance will then be seen at the input terminal. So if I ask you, okay, let me just try to wrap this up a little bit. So if I ask you this question in a quiz, so what is the, oh, I didn't get the answer. So what do you expect? In most cases, we assume that source resistance was supposed to give you low input resistance. But if this is the case, if I have an ideal current source load, I'm looking in from input. Based on this equation, it tells me that if this is infinite, the whole equation goes to infinite. So this will dominate your overall input resistance. Okay? Even though there's an attenuation effect, but it will then still make it fairly large. If this is large. Only when this is small, then you see this, the left-hand side. When this is smaller than this, then you see 1 over GM. Okay? So we're going to wrap up on the last discussion on common gate stage. So that is the impact of RS if there is a source resistance connected to the input terminal, or the source resistance effect when you're looking at Vx. So what happened is that if this is included, this will be similar to our discussion with source degeneration. But let's just write it. So the way to test this is RL prom. So in this case, we could write down that your Vx equals to the voltage, let's say this. So let's define the voltage here as the source voltage. So this will be Vx equals to source voltage plus the current across Rs minus Gm VGS times RO. So that's the current going down is Vx Rx. And then minus this part will then be the voltage across output resistance. That would allow us to define our output voltage Vx. And Ix will then be Vs Rs. And we know that this is minus VGS. Vs is minus VGS. In this equivalent circuit, then simply put it back into the equation. Then I get Vx Ix. This is R output. Will then be approximately as Rs plus RO plus GMRO Rs. So you do the same arrangement and exercise, and then we get the results. RO 1 plus GM. Okay? So you actually see that if I'm summarizing with the previous table, you will see that if I'm looking down my RL, I want to put them in parallel to compare. So you will see that it's originally 1 over GM, then the effect of RD is being attenuated by a factor of GMRO. So that's output terminal. If you're looking down from the, looking in from the input terminal, sorry. If you're looking in, this is from source. From source up. You look up, and then the effect will be its original 1 over GM, and then whatever the loading resistance being attenuating by a factor of GMRO. On the other side, this will be R out from drain down, looking down, I should say, from drain looking. If you're looking down from drain, downward, what happened is the R out prom will be, let me just use an approximation just to make it easy. So you will then have your original output resistance, which is the green one, bridging the two, plus a GMRO. Okay? So it's being amplified. See, this is being divided by GMRO. This is being amplified by GMRO. So that's why we typically refer to as a impedance transformation. You see amplification effect if you stacked up from the bottom. You see attenuation effect when you're looking down from the source terminal. And this relationship is very useful when we talk about when we have multiple transistors stacked together. So we're going to talk about that type of structure in what we call a cascade. It's like a Tatum pole. You have a multiple transistors stacked together, and these effects will then play important roles when analyzing its overall gain under different operation conditions. Okay? So let's do a summary as well. So let me do the summary on the left. On a common gate stage. As I said, a common gate stage for a more general term, it will look something more like this. To write a more general term, it will look something more like this. I'm going to include RS down this way. So this will be my input terminal. This will be my output terminal. To be a more general consideration. Okay? So if this is the case, there's various considerations. First of all, the most simple one is that you ignore. Let me think about which way. So first case is RO is infinite. So there's 3 scenarios. I'm going to write down the so this is when RS is 0. I should make a better table. So looking at basically 3 parameters as well. Okay? So 2 main categories. One is you assume RO is infinite. and whether there's RS. Okay, so this is RO. If you include RO, it's finite. So we're going to talk about, of course, gain, voltage, input and output resistance. So input Rn. So I want to highlight the most simple case. We'll go back to the most simple case. It's a 1 over Gm. It's a low input resistance case. Your output is simply RD will determine, and your voltage gain is Gm RD, which is a non-inverting gain. Right? This is the most simple one when you don't consider there's a source of resistance coming in. If source resistance being incorporated, your input resistance, I should say, I just write down the gain part. So the most effect is on the gain, 1 plus Gm. And its gain, if it's stacking it up, will be RS plus. If you're assuming that it's coming in from here. Okay? And then I would then consider my output. There's no impact on the output. The source is because I'm assuming there's no bridge in between the two. Okay? So on the right-hand side, we're going to use the results that we get on the input and output resistance. So the input and output resistance for the input terminal, it will be 1 over Gm plus RD Gm. If you want to include RS, it will just be an add-on. If you want to include RS from the input terminal, if I'm looking in from here. Okay, it will be just an added term. From output terminal, you will then have RO plus 1 plus. Let me just use the same approximation, assuming that GMRO. So the resistance looking down, the source resistance being amplified by a factor of this. And if you want to include RD, to be more precise then, it will be the resistance looking down, RL prom in parallel RD will be your ultimate resistance. So this will depend, depending whether you want to add external resistance. Okay? And including RS, it will be very similar to this. So this will be very similar to that. Okay? If it's RD, mostly still RD dominate. The main effect will be on the impedance itself. The overall gain will be dominated by RD in most cases when you discuss the gain. Mostly, let me say this. Anytime we discuss the gain, it's typically dominated whether by the low resistance. The lowest resistance in this pathway is typically RD at the output terminal. And then the source degeneration effect will have most important impact. Therefore, if you're looking at the output gain, it will be very similar to that when RS is being included.
It's set to 1.1 amp. And under saturation, U and Cx, W over L, VGS minus VGS. Okay. So I know this to be 0.11. I know this number, and this is 1.1. So I should be able to solve for W over L. So the W over L in this case is 400. It's a relatively large device. Okay? The reason why you can actually use different now, but you want to make sure that your length it has to be larger than 0.18 because we're using 0.18 technology. 1.8 voltage simply implies that you're using 0.18 technology, so your L must be larger than. Make sure that your L is much larger, larger than 0.18. So this means that this is a unit of micron. Okay? Now the reason why you have a relatively wide transistor, as I said, because MOSFET is not a very high drivability device. In order to provide such low input resistance, you typically need relatively large width in your transistor in order to provide low resistance, low input resistance. Okay, so that's sort of expected. So then, once we have all the number, we need to determine rest of the resistors. But typically G1, G2, because the RD doesn't really matter, just to make sure that it's not set it up to saturation. So next thing we need to do is to find out, we already know W over L, so then we need to find out what is my voltage level at this terminal, VG. So VG will simply be ID RS plus VGS. So IDRS is, I know it's 500 ohm times my current level is 1.1 volt plus VGS is VTH plus an overdrive. I already know my overdrive is 0.1 volt. Okay? So this will be 0.55 plus 0.5 plus 0.1. Okay, this is my threshold voltage. The overdrive comes here, right here. Okay, GM determine your overdrive under a fixed current. So then you can then get this 1.16 volt. So once you know that, then we can determine, I already know that I need this voltage to be 1.16 volt, therefore I should be able to determine RG1 or RG2. So I already know that RG1 plus RG2 equals to 1.8 volt divided by its current, which is, remember we already said it at the beginning, I1. So this will then be 180 k ohm. So what you need to do is simply set it up so that RG1 is 64K and RG2 is 116K. So that I could set it to 1.16 volt at this terminal. Okay? Yes. This one? MA, sorry, yes. Okay. Oh, yeah, this one. Sorry. Okay? Good. So once we have these numbers, we can then find out my biasing condition. Just to make sure that you didn't fall asleep. So finally, you're only one parameter left. We already determined the size of the transistor, all three resistors, so only one more resistance undetermined. This one is somewhat arbitrary. You can determine, because we didn't request for a voltage dip, we only request for input impedance. So this RD, you just need to pick a number which will make sure that this device will be operated in saturation. Just don't pick a number that will make this device under linear regime. So what is the limitation on RD is that my drain voltage, let me use this. So think about it, the VD must be higher than, your voltage must be higher than VG minus the threshold. So must be higher than VG minus VTH. So VG is 1.16 minus VTH is 0.5. So this would be 0.66. Did I get it right? So you want to make sure that ID is higher than 0.66. Therefore, your voltage at the drain is VDD minus ID RD. Okay? So then you want to pick a RD. So this will be 1.8 minus right. So your RD must be smaller than this number. So you just put in the numbers and you should have make sure that this device, you can ensure that M1 will always be in linear region. So that's the only thing you need to figure out. You can pick a number which will fulfill your RD. I should say RD should be smaller than this. Okay? To ensure that it will not saturate this, it will not push this down into saturation. So I didn't have a number, but just to make sure that when you pick RD, make sure that it's correct. Okay? So once we have a better understanding of, or go through an example, hopefully you get a sense of how you approach a design problem and what are the parameters that are linked together. The bridges allow you to determine each one of these parameters. Okay? So, so we're gonna move on to the next. We're gonna talk about the next stage, which is a common drain structure. So as I said many times, a common drain device, common drain stage is often referred to as a source follower because the source follows the gate. So it's called the source follower. It's very, very common. And as I said, there's billion, in your cell phone, you have billions, millions, 600 million pixels, you have 600 source followers. Okay? So each one of your sensor pixels has a common source structure. So it's a very, very commonly used structure, and especially it's commonly used for, as I said, if you want to bridge it out, there's two commonly used two applications. One is when you need to drive external element out of the circuit. So like the example we use that if you have a circuit which you want to push the signal out into a speaker, so that's an external component out of the circuit, then you need a source follower to drive. The other example that I use typically is very commonly used is that if you need to drive large internal capacitors. So when you experience large internal capacitance, especially happen when your circuits are placed in an array. The example that I use is in a CMOS sensor. So anytime you need to push large capacitance or external components outside the circuit, then you need a follower circuit to typically referred to as a driver. It's a current driver, allow you to push your signal out. So the basic idea is not to amplify the signal. The basic idea is to follow the signal, but then provide a lot more power, a lot more current to drive whatever the node is. So you want the following effect, and you want the drivability. So common drain stage is fairly straightforward, that we have already discussed a little bit on the emitter follower, but I'm just going to use this approach. So for common drain topology, of course, my drains are common. And then it's my input is at the gate and output is pulled out at the source. So this is a simple source follower common drain stage, or a source follower stage. And you can refer this to as a source resistance or loading resistance. It will depend on whether you're opening it directly to drive whatever is needed, or it's part of your driving. So I'm just going to simply just use it as a low resistance. Okay? So to analyze the performance or behavior of this stage, we're going to use the small signal equivalent circuit. Of course, you can draw that very easily now, supposedly. So you start with so we start with the gate. This is where the input is, V in. And this is the drain where we ground it. AC ground, RO, GM, VGS. Okay? And then at the bottom, you then connect it to the load, which is R load, and my output is here. So I'm just highlighting where the input is and where the output is. So this is my input, V in. There will be something here to a reference ground. That's V in. V in is not, so I'm sure it's not misleading. Okay, so once we have a small signal circuit, we could actually simply write the output and input response. So VL will simply be whatever current is flowing through this terminal, and you can actually fold this resistor downwards because it shares a common source terminal, the other ground. So the way to think about it is a current, which is GM VGS, and it's flowing through a resistor R load in parallel R load. Okay. So if you can see the parallel same terminal, that's so they are in parallel. So what about V in? The next equation is to writing down V in. So V in will simply be VGS plus VL. Right? VGS, and this is VL. This terminal is VL, so VGS, VL. And it will simply be VGS 1 plus VGM. So you see very familiar results. Once we have this equation, you can simply divide input and output to get the voltage gain. So my voltage gain is defined as VL, V in, both in terms of VGS, therefore you can eliminate VGS from the top and the bottom numerator and denominator, so you get GM low and parallel RO, 1 plus GM load. Okay? So that could be quite straightforward. So we always need, as I said, just a reminder, we're going to have our long-awaited quiz number 5. Yeah, quiz number 5 next week. It's on schedule. We'll then have something, not necessarily this question, but something very similar. What you need to know is that we're going to have a few of the conceptual questions, and then we're going to have one calculation questions. Start from, you need to find out DC biasing current, input-output resistance, and that sort of input-output resistance and voltage here. So these are just the simple, basic principle, basic questions you need to answer in a single-stage circuit analysis. So we already answered our voltage level. Voltage gain, of course, you need to look into input and output resistance. These are typical problems. So input, there's no discussion what is input resistance. Yes, of course. So what about output resistance? If you're looking in from the output terminal, what do you expect on seeing? If you're looking in from the output terminal, I'll get, let's just go through the, how to actually get R out. So find R out. You have input grounded. This will then be R load. And GM VGS. And then RO, grounded. Looking in from here, I'm giving a test voltage again. If you don't know what to do, just do this. Okay, VXIX. So what are the current components that will contribute to IX? I will then have VX R load plus VX RO plus minus GM VGS. Right? The current coming in will be this branch, and that. There's 3 branches of current contribute to IX. And because I know what is VGS, VGS equals to, in this case, because my input is grounded, therefore VX equals to minus VX. So you simply insert that, we should be able to get my IX. I'm just writing it over here. Will be VX R load RO plus okay? So then you could actually write your R out. My definition is VX IX will simply be 1 GM plus RO plus and this can be rephrased as 1 over GM in parallel RO in parallel RO. So that's my output resistance should be able to attain. This good. So let's look at what are the ways of setting it up. What I meant by setting it up is how do you actually set up your, in this case, what is the typical stack you wanted to reach? There's actually 2 parameters. We already know that my input resistance is infinite, So typically what we wanted to demonstrate is drivability as well as gain. These two are actually linked together. So drivability meaning that how well can I push my signal out? That would then determine by your output resistance. And of course, the voltage gain, you want to make sure that it's close to 1 as possible. Therefore, how do you set it up to a certain point, allowing it to deliver the specification, meaning its gain and its output resistance. So let's just briefly look at two of the biasing examples. So biasing methods. So the first one is that I can simply use a resistor to set up and to get my gate voltage, to determine the gate voltage. This is VDD. So to determine my gate bias, I'm simply going to use the single stage self-biasing stage with an RG in between. And then this is my input. So there's two coupling capacitors to couple input and output, and this simple stage will then be determined, DC bias will be determined by VDD and RS. So there's two parts in analyzing this type of circuit. One is to determine the current. So you need to determine ID. So that's the DC part. Once I have the ID, the second thing you do is then find out GM, or those parameters, and then determine your voltage gain as well as output resistance. I already know my input resistance is infinite, so in this case it will be RG. Okay? Okay? So how does one determine, if you want to analyze the circuit, how do you determine your current? So basically one equation is this. Because there's no current flow, so there's no voltage drop on this, I know my gate voltage, VG, equals to VDD, based on this biasing scheme. And VDD equals to VGS minus plus ID. So you're simply using the choosing of RS to determine your drain current. Okay? And drain current is determined by this equation. So you solve for, use not iteration, solve for, using this current equation to solve for ID or solve for VGS. Voltage equation. The other is voltage gain. This voltage gain, in this case, will simply be GM or S1 plus GM. Okay? So basically in this design, what you do is that you simply pick an RS to determine ID, and also this RS will determine your voltage, I should say your output voltage gain. And the output resistance, let me write down. In this circuit, the input resistance will be RG. Output resistance will be that. It's 1 over GM and parallel RO and parallel RS. Okay. So this is the same problem with designing your DC bias using a resistors system. The main problem with this type of system is that your AC behavior and DC behaviors are intertwined together, because once you determine, you might determine this is the best place to stand. Therefore, you determine your Rs. Then there's no freedom in determining your output resistance, or small signal counters are actually fixed once the biasing point is fixed. So that it allows you very, very little freedom independently determine where's the best place to stand, and the performance when you stand right there is actually linked together. So it's very rare you can get the optimum point. And this is the way we bias our system. Therefore, in most of the integrated circuit solution, is actually a much better way of doing this. So a better example, I don't think we have time to move on, so just make sure that. 所以我简单的用中文 summarize 一下，就是针对这个 common 这个 source power 的 circuit 呢，我们刚才有讲，就是它最常见的应用就是你要提供高电流去推动某一个元件，或是特别是小电阻或是大电容。大家想象为什么是小电阻大电容呢？就是如果你有一个 component 电阻非常小，那表示什么呢？表示你要让它看到电压变化的时候，你要让它看到电压变化，你要很大电流啊，因为你的电压是 IR 嘛 ，R 小的话 I 就要大，否则你会看不到它的波动。所以呢，就是这小电阻，那大电容一样，大筒子啊，看看大筒子怎么样的反应？灌水要灌多，你灌一点点水，那个筒子根本没有反应，所以你看不到反应这件事情。是为什么我们要做 driver？ 就是说你今天没有做这件事情，你给它小电流，然后你去推一个大电容，它就不会动。它不是不会动，如果你给它无限时间，它会动。但通常我们还是有一个时间的需求嘛，就是这个跟频宽有关，跟速度有关。所以我们刚才讲说，大部分这个 source power 的，你想象它的事情就是它提供一个大水管、大水龙头。那这大水龙头有两个很重要的事情，就是它的 drivability， 就是它能够提供多大的电流去推这个大水桶，或者是小电阻。那或者是呢，它一个是推 external element， 就是我们上次举的那个 speaker 的例子，或者是呢，你 internal 如果有非常长的线，如果说你在 IC 里面，特别大家知道。你如果大的结构，通常是线拉很长，在阵列里面，我刚才举的例子就是手机里面有100万画素的 CIS， 那每一颗里面都有一个 source power， 所以我只是告诉大家说它非常非常的 useful。那它为什么要做这件事情？就是如果你是大阵列的话，你一条一条阵列，那你要去推每一条，你是跟很多人共用，譬如说100万的假设啊，就比较小的 rate， 大概是好几千或上万颗是共用一个走道，那这个走道当然就是相对来讲就是比较大，所以你要怎么推这个走道呢？一样你就要有个 driver， 所以为什么每一个里面都要有个 driver， 就是去把你的讯号，你 sense 到的讯号把它推出来，推到这一条走道上面，大家可以看得到这样子，所以这个非常非常常用。那我刚才要讲的是说，好，那所以我们就做小讯号的分析。那我最后要讲的是说。如果你要做这种 stage 的 biasing 的话，它最重要的就是如果做电阻 biasing， 这个是所有你做电阻 biasing 的一个比较大的问题，就是你站在什么位置，就是你想要决定 ID， 那它是由 RS 来决定的，但是 RS 同时会影响你小讯号的行为，所以这两件事情分不开。也就是说，我觉得今天我做了一个大的 survey， 说我就是要站在这个位置上面最好。可是站在这个位置上面，同时站的位置这个点也会影响到我的 behavior。那在这个小讯号的行为，这两件事你不能够独立设计的时候呢，就会有很多 constraint。所以我们等一下会来讲说，那所以真正在 IC 里面，我们通常也不会用电阻去设计，因为电阻刚才讲它会互相干扰，就是你没有办法独立的去最佳化它。那如果不行的话，那用什么比较好的做法？就是用current source biasing， 那我们后面其实第9章也会看到怎么去做这些 current source， 其实是有非常好的方法去提供一个非常稳定的biasing 的系统。那这个我们可能到第9章才讲，但是大家要记得，就是它的最重要的好处就是独立去最佳化，就是你在这个点上的 performance 这件事情跟你站的位置是没有关系的。这样的话就可以两件事情都可以同时最好。那我们休息一下，然后回来呢，可以把第7章调完。OK。Here. I'm not going to draw there. So this is your output. So how do you determine? You simply use a current source. So how do you actually realize a current source in an integrated circuit? Here you simply use another MOS with a fixed bias. So this would then resemble a current source, right? So this would then, so basically as we already know, in this design you typically want two parameters. One is your biasing ID, would then determined by, let me write down, this is the M1, this is the M2. Okay, so you use the M2, the circuit underneath, to determine the biasing current. ID equals to I1 equals to 1/2 mu NCX WL2 VB minus VTH. Okay, so this will then give you the first set of your current through this current source. So I could actually very easily set the level of current through simply by adjusting my biasing level. So this is to set your operating point. So the next thing is then what is its voltage gain? So its voltage gain is then the GM. So at this external terminal, what you actually see is that there's a output. This in small signal model, this would then equivalent to RO2 because you're looking down from the drain. Therefore, the gain will simply be GM. Yeah, oh, sorry. There's two BMs. This is BM. Sorry. Okay, so your voltage gain will simply be GM RO1 and RO2 1 plus GM RO1. Okay? So as you can see, there is actually benefit of doing this design is that I will then have my operating point set independently by this current source with setting up, typically by setting up your biasing voltage level, so you can set your current level. And the other thing is that you can then provide your output resistance. So your output resistance will then be, the key is actually not necessarily gain because we're not driving anything yet, but output resistance will then determine the key parameters 1/GM. So it will be, I should say it should be RO1 until RO2, and it should be 1/GM1. And how do you determine 1/GM1? This will then be determined. So how do you design GM1? Determined by W/L1 and ID. Okay? You can use these two parameters to set it to a particular level that will meet your spec. Okay? So the next exercise we're going to go through is an example that we have already studied in bipolar, the discussion of emitter follower in bipolar. So we're going to use the same example. So the example is to study the effect of adding the source follower stage. As we already mentioned previously, if you simply having a common source stage, I'm having a common source stage that's already designed, Okay, so this is the common source stage with a voltage gain. Using the same example of 20. And then I know my GM1 is 0.02. This is designed with a GM1 of 0.02. Okay? So if this is the case, I'm driving it directly. So the first one is I'm simply going to just drive it directly, push the output to a speaker with RSB. I'm directly connected to a, not directly, but just to decouple from AC and DC. So anyway, I'm just pushing it out directly to, this is my output, this is input. I'm directly connected to my output without having a buffering stage to RSB, which is A ohm. So we already know that if this is the case, your voltage gain, this is not open anymore because I'm connecting to a very small resistance. As I said, if this is my design, the gain will simply be GM, approximately, I'm just going to, the gain will be GM1 times RD in parallel RSB. Okay? So we know that this is much, much larger than this. This is A ohm. So you're simply having 0.02 times A ohm. So that'll be a very small number, 0.016. So you're not amplifying your signal is actually being attenuated, it's not an effective amplifier. If you connect it directly, even though I have internal gain, it doesn't reflect at the output because there's no buffer within the two. So in order to maintain whatever gain through this common source stage, to maintain this 20, see how much we can save. So you add a buffering stage. So we can add a buffering stage. So this will then become a two-stage structure. I have the first stage will still be my original design, M1. So we know that again this is 20. And for this stage, I know my input resistance is infinite. My output resistance is R2. So this is the description of your first stage. And then this is connected to a follower stage. So this is M2. And it's connected to a follower stage. I'm not going to do particular biasing design just to set it to directly to the speaker. Okay? I'm going to ignore, just use capacitance to make sure that it's biasing at a particular location. Okay? So this is what we'll be using through a buffer. So once you have a buffer, I will kind of need to write down what happened at the second stage. So for the second stage, you have a voltage gain, will be GM RSP 1 plus GM2 G2. Okay? We already know that. And input resistance are in, let me label it as this is 1. Since I have two stages, just to make it clear. So my Rn2 will be infinite. My Rout will be 1 over GM2 in parallel RSP. Okay? So what you can do is that in order to get your overall input and output, so this is my input, this is my output. So you can actually draw the two-pole model simply by using this. Okay? So I'm going to do this input stage. So that I have a common source stage with a voltage gain AVO1, V1. Okay? And then this will be RO1. This is RA1. RA1 is infinite, therefore you don't need to. So this would then be connected to another V1. And then AVO2. V2. So I have my, just to be clear. This is my first stage where RA is infinite, RA1. So this is the common source stage. And then on the right is the source follower stage. So I have a source follower stage, which would then be okay, this is my source follower stage. So here is the input, here is the output, and this is the ground. Okay? So then for the input stage, well then, if I want to get the overall response, what is typically being done is that your VL, you could actually start on the right-hand side. Your VL, because we already include RSP inside, so you could simply use an open circuit result. So your output will simply see AVO2, V2. Okay, right? So what is V2? V2 is the division between the two. But then because my input resistance on the second stage is infinite, therefore you don't even need to know what RO1 is because there's no dividing factor. I'm taking in whatever the voltage here because I have infinite input resistance. Okay? So this will simply be your AVO2 times AVO1. And times V1. And because V1 equals to Vn, therefore it's simply the AVO2 AVO1 times Vn. So my overall gain will simply be the multiply of this 2. Right? So my overall gain is going to give the absolute value. Will simply be AVO1 times AVO2. Okay? Oh, I forgot to do the key parameters, sorry. So I'm assuming my GM2 is already designed. So I'm assuming that the biasing is setting up GM2 10 times larger, so which is 0.2 amp per volt. So let's assume that this is given, then I should be able to get my ultimate result. I already know that my initial common source state is designed as 20, and this will be 0.2 times 8 ohm, 1 plus 0.2 times 8. Okay? So you can simply use GM2 inserted into here, given that my VSP is AM. Then the attenuation factor of this term, this is 20 times about 0.61. That's 12 volt. So you still maintain about 60% of your original design gain, even with driving such a small resistance at the load. Okay? The typical source follower, if you're designing a source follower, the typical stack is somewhere around 50% to 80%. That's a typical number. It's very hard to get, if you're driving a very small capacitance, large capacitance or small resistance, the typical target is around 60 to 80. Okay, 60 to 80%. That's a typical number. So if you're getting a very, very low number or very high number, you're supposed to read it, just to check whether if you get all the parameters right. Okay. So before we wrap up chapter 7, I'm just going to give a small summary. So MOS. So first of all, we talk about a common source. In, out. Like something like this. So common source is typically, if you look at in a analog circuit architecture, common source is very commonly used as, we refer to it as the gain stage. If you use the example above, that's the part that we're actually providing most of the gain. So its unique, very good feature, especially for MOS device, MOS stages. You have infinite input resistance. So anytime you're dealing with voltage amplification, that's the most ideal thing you want. You want to take in all the voltages without having any loss internally at the series resistance. And its output resistance typical in the range of, depending on the the internal output resistance and of course your loading biasing resistance. And it's an inverting stage. Okay? So uniquely, it's a gain stage providing a gain of GM or out as sort of parameters. So for common gate, you're simply having structure like this. We have already reviewed it. So this will be your fixed bias. And then my input here, output as a drain. So what is the best feature of a common gate stage is that it has low Rn, or you typically want to design it to meet certain resistance level. Low Rn is in the order of 1/Gm. So through designing your size of the transistor as well as biasing, you can set this to meet a certain low impedance target. And then, of course, Rout, if you're ignoring all the components, Rout will also be typically determined by Rd itself, the biasing component on top. If we need to consider more detailed effects, we're going to talk about it, especially in cascaded structures. Okay? So lastly, you have the follow circuit. So source follow circuit. It will then be fixed bias typically at VDD. And then it will be something like this. Your input is right here, the output is right here. Okay? So if this is the case, then it will then also have, this will be a buffering stage. Buffer, or we call it driver circuit. You need a driver circuit. Driver meaning that driving current. You provide current drive, large current to fill up your tank or to push up a low resistance component to reflect its voltage level. So it also have input resistance, which is infinite, and its R out should be in the order of 1/Gm. Okay? So low output resistance, high input resistance, that's the buffering stage. One thing I want to mention, I probably briefly discussed this when we discussed the body effect. So in these three structures, I might have a quiz question. Which one actually is subject to body effect the most? Or which one does not subject to body effect? So by default, I want to mention again, all of the circuit will have their body grounded. This is body is grounded, the body is grounded. So all of them have their body grounded, right? So which one will not subject to body effect? Will not.